buried under 20 kilometers of ice. On a moon smaller than ours, there is an ocean. Not a frozen relic, not a trace of something that used to be. A real, liquid, saltwater ocean, warm enough to stay fluid, vast enough to dwarf every ocean on Earth combined. And for a long time, that's all we could say. We knew the ocean was there, but we had no idea whether anything interesting was happening between that ocean and the frozen surface above it. Was the ice shell a sealed lid, or was material actually moving between the two? Now we have an answer, and it's a big one. If you're looking for life beyond Earth, Europa is probably the most exciting address in the solar system. It's one of Jupiter's 4 large Galilean moons, and it's completely covered in ice. But unlike, say, a frozen comet drifting through empty space, Europa's ice is warm. Jupiter's immense gravity is constantly squeezing and stretching the moon, a process called tidal heating. And that friction generates enough warmth to keep a vast ocean liquid beneath the surface. So you've got liquid water, you've got energy from tidal forces, and if you could show there's chemistry happening, specifically carbon-based chemistry, you'd have the 3 pillars that, as far as we know, every form of life requires. The problem? That ocean is hidden under kilometers of ice. We can't just scoop up a sample. So scientists have had to get creative, using telescopes to read the chemistry written on Europa's surface and work backwards to figure out what's going on underneath. That's where the James Webb Space Telescope comes in. In a new study published in March 2026, a research team used JWST's near-infrared spectrograph to perform something called spectral decomposition on Europa's leading hemisphere, the side that faces forward as it orbits Jupiter. Think of it as chemical fingerprinting at a distance. Every molecule absorbs and reflects light at specific wavelengths, leaving a unique signature. By analyzing 9 separate spectral bands covering water ice, carbon dioxide, and other compounds, the team could essentially peel apart the different chemical layers on the surface and map exactly where each one sits. Now, carbon dioxide on Europa isn't brand new. Back in 2023, 2 separate studies using JWST detected CO2 concentrated in a region called Terra Regio, a geologically chaotic area where the surface looks like it's been cracked apart and refrozen. That was already exciting because it hinted that the carbon might be coming from the ocean below rather than being delivered by impacts from space. But the new study takes it much further. Using this spectral decomposition technique, the team found that the CO2 enrichment isn't confined to Terra Regio. It spreads across multiple chaos terrain regions in a broad lens-shaped pattern. And here's the critical detail. Everywhere they found higher concentrations of CO2, the ice itself had unusual structural properties. It didn't look like normal radiation-battered surface ice. It looked like it had been reworked from below. This is the key insight. It's not just that carbon dioxide is present on the surface, it's that the places where it concentrates are the same places where the ice shows signs of being refreshed by material from underneath. The 2 patterns overlap almost perfectly. So what does this tell us? 2 huge things. First, there is carbon in Europa's ocean. Carbon dioxide doesn't just appear from nothing. For it to be showing up on the surface in patterns tied to geological activity, carbon-bearing material has to be coming from the interior. Whether the CO2 formed directly in the ocean or was produced when ocean-derived organics reached the surface and got hit by radiation, either way, carbon is part of the ocean's chemistry. Second, the ice shell is not a sealed barrier. Material is actively moving between the subsurface ocean and the surface. There's ongoing chemical communication through the ice. Scientists call this surface-interior exchange, and it's one of the most important questions about Europa. And there's a fascinating twist the study uncovered. The researchers suggest that the distribution of CO2 on the surface doesn't just reflect where material gets pushed up. It also reflects where the surface is capable of holding on to it. The microstructure of the ice itself might determine which volatiles are retained and where. So you're seeing the combined fingerprint of two processes: emplacement from below and retention at the surface. This new study fits into a bigger picture that's been building over the past year. A separate JWST study from 2025 found that Europa's surface ice is crystallizing at different rates in different places. In areas like Terra Regio, they detected crystalline ice both on the surface and at depth, something that shouldn't happen if radiation bombardment were the only thing shaping the surface. See, Jupiter's magnetic field traps enormous amounts of charged particles, and those particles constantly slam into Europa's surface. This radiation turns orderly crystalline ice into disordered amorphous ice. If nothing else were happening, you'd expect to see amorphous ice everywhere. But they're finding fresh crystalline ice, which means something is actively resurfacing from below, pushing warm water and dissolved materials up through the shell. The process might be driven by diapirs, warm plumes of slush and water that rise through the ice like slow-motion geysers. And this resurfacing happens fast. Some estimates suggest that in certain areas, the radiation can break down fresh ice in as little as 15 days. So Europa is essentially locked in a constant cycle. New material wells up, freezes, gets hammered by radiation, and then gets refreshed again. It's a far more dynamic world than anyone imagined. All of this sets the stage for what might be the most anticipated planetary mission in a generation. NASA's Europa Clipper launched on October 14, 2024, and it's currently on its way to the Jupiter system. After a gravity assist from Mars in early 2025, it's scheduled to swing past Earth in December of this year, 2026, before heading out to Jupiter, arriving in April 2030. Starting in 2031, the spacecraft will make 49 close flybys of Europa, coming as close as 25 kilometers from the surface. It carries ice-penetrating radar, high-resolution cameras, a thermal imager, and instruments designed to sniff out the composition of Europa's extremely thin atmosphere. It's the most comprehensive toolkit ever sent to study an ocean world. And here's why the JWST work matters so much for this mission. The chemical maps that Webb is building right now are essentially a treasure map. They're telling Clipper exactly where to look. The chaos terrains, the CO2 hotspots, the places where the ice is freshest. Those are the targets where Clipper's instruments can dig deepest into the question of what's really going on beneath the shell. We started this video with a simple image: a hidden ocean locked away under ice, orbiting a gas giant hundreds of millions of kilometers from Earth. And for decades, that's where the story stalled. We knew the ocean was there, but we couldn't reach it. What's changed is that we don't have to reach it, because it's reaching us. Carbon from that ocean is being pushed to the surface, frozen into the ice, and read by a telescope floating at the second Lagrange point, 1.5 million kilometers from Earth. We are, in a very real sense, tasting Europa's ocean from across the solar system. And in 5 years, a spacecraft the size of a basketball court will be flying through the plume shadows of that little moon, scanning every crack and chemical signature with instruments we built specifically for this question. Is Europa habitable? We don't know yet, but for the first time we have the tools. And now, the map to find out. If you enjoyed this, consider subscribing. There's a lot more solar system story to tell, and you won't want to miss what's coming.